Welcome to Effortless Math Channel. Today, we're going to learn how to represent rational expressions in graphical form. What are rational expressions? Rational expressions are fractions where both the numerator and the denominator are polynomials. Another way to think of these expressions is as a ratio of two polynomials. And here are some examples. 2 over x, 3 over x plus 4, and 5x minus 1 divided by x squared plus x minus 2. Here's an example of how a rational expression may look on a graph. Oftentimes, the curves will end up looking like this, where there are clear gaps in between. So what do these gaps mean? Well, take a look at the y-axis. The curves never actually end up touching this y-axis, and so it's as if there's an invisible line where it is that they don't touch. And this here is referred to as a vertical asymptote. On the other hand, the curves do the same with the x-axis, and so this here is a horizontal asymptote. And in this case, because they don't touch either the x or y axis, these curves do not have x or y intercepts. This will not always be the case with rational expressions. So how do we figure out what these vertical asymptotes are? Well, first off, what is a vertical asymptote? A vertical asymptote can be represented by the line x equals a. And this only exists if the graph approaches this line and it never actually touches it. So the curves increase or they decrease or they do a bit of both. This can apply to both sides of the graph or only to one side. So the way it is that we determine what these asymptotes are from the given function is by setting the denominator equal to 0, and then we can solve for x. The caveat is, however, that this value that we solve for, x equals a, which is representing a number, is only valid if when plugged into the numerator, it doesn't make the numerator equal 0. So let's actually do some examples based on the examples that we had before. Let's start with 2 over x. Let's set this denominator equal to 0 and solve for x. So then we'll end up with x equals 0, and here it's pretty straightforward. X equals 0 is our potential vertical asymptote. Before we can declare that this is the case, we have to actually check. So we do so by inputting this value into the numerator. But again, this example is pretty straightforward because there's no x in the numerator. Therefore, we can't plug in x equals 0. So x equals 0 is the vertical asymptote for this rational expression. Let's now do a more complex example. So we'll follow the same steps as before. Let's set our denominator equal to 0 and solve for x. In this case, we have a polynomial that has 3 terms, and so we'll need to factor in order to solve for x. Perhaps we'll end up with one answer, perhaps we'll end up with 2. But let's see. Here we have to do the AM method. The AM method is the method in which we find two factors, two numbers that add up to the coefficient that is next to the x, and two numbers that also multiply to -2, the term that does not have a variable next to it. And so those two factors end up being +2 and -1, and as we have an x squared here, we'll carry down the x squared, 1x here, 1x here. Then what we can do is we can do something called teeing off so that we can separate our two parentheses, our two bubbles, as I like to call them. And so we can have x plus 2 equals 0 and x minus 1 equals 0. Here then, when we do algebra for both of these equations, we'll end up with x equals -2 and x equals 1. So again, these are going to be our potential vertical asymptotes, but we have to double check. So let's go ahead, take the numerator, and plug in each of these values into the numerator to see if the numerator ends up equaling 0. This then would invalidate these asymptotes. So when we plug in -2, we get 5 times -2, which is -10. -10 minus 1 is -11. So this checks out. That doesn't equal 0. Let's try the next. Let's plug in 1. 5 times 1 is 5. 5 minus 1 is 4. This again checks out. This does not equal 0. So we have these two vertical asymptotes, x equals -2 and x equals 1. Now let's look more into horizontal asymptotes. What are they? Horizontal asymptotes can be represented by the line y equals b, where b is going to be equal to some number. And this only exists if, as we mentioned before, as the graph approaches this line, the graph increases, decreases, or does a bit of both. So this can apply to both sides of the graph, both curves, or only one side. And there are no limits, no bounds. So let's use this function here in order to figure out what the rules are. How do we figure out what a horizontal asymptote is from the function provided? Here we have c and d, which are going to be coefficients, and we have x to the n power and x to the m power. N and m are exponents, but they're special exponents. They are degrees. The degree refers to the highest exponent. So for example, if we have an expression x squared plus x plus 1, the squared is the highest exponent. Therefore, 2 would be the degree. So we have to compare n and m, the exponents, specifically the degree, the one that applies to the numerator and the denominator, in order to determine just what the horizontal asymptote is. If n is less than m, the x-axis is the asymptote. If n is equal to m, then we have to divide the two coefficients, which in this case are c and d. These are, again, the coefficients that correspond to the degrees of the numerator and the denominator. However, if n is greater than m, then there is no horizontal asymptote at all. So let's actually go ahead and apply these in some examples. With 7 divided by x plus 1, let's start first by identifying what the degrees are. In the numerator, there's no x term at all. There's no x variable. Therefore, the degree, or n, is going to be equal to 0. For the denominator, there is an x term. There is x. There's no visible exponent there. However, we can assume that the exponent is equal to 1. Therefore, m equals 1. The degree is 1. So let's go ahead and compare n and m. Is n less than, greater than, or is it equal to m? Well, 0 is less than 1. And so n is less than m. Now let's go back to our rules. What does that mean? Because n is less than m, the x-axis is the horizontal asymptote in this case. Now let's go on to a more complex example on the right. And we'll follow the same steps. Let's examine our numerator and denominator. What are the degrees? For our numerator, it's going to be n equals 2. And for our denominator, it'll also be 2. M equals 2. In this case, when we compare the two exponents, or two degrees, they are the same. Therefore, n is equal to m. Now, what does that mean? That means that in order for us to figure out what the horizontal asymptote is, we have to divide the coefficients. The coefficients in this case, again, they're going to be next to the variables that correspond to the degree of the numerator and denominator. And so the exponents are here, and so the coefficients will be over here. On top, the coefficient is 5. On the bottom, it appears as if there's no coefficient, but we can assume that there's a 1. And so let's go ahead and plug into our equation, y equals c over d, or y equals the first coefficient divided by the second coefficient. Y equals 5 divided by 1. And so that will be equal to 5. Therefore, in this case, y equals 5 is our horizontal asymptote. Now, this is the last piece of the puzzle. Usually when we graph, even beyond just graphing rational expressions, when we're graphing lines, parabolas, exponential functions, we find x and y intercepts. This way we have points to go off of when we're graphing our curves. And the rules are the same, with a little bit of a twist. To determine the x-intercepts, which are also known as our roots, we can set the numerator of the rational expression equal to 0, and we can solve for x. But there's a caveat to this. These x-intercepts actually work, they're only valid if they don't make the denominator equal to 0. So you have to check that before you move forward. To determine the y-intercepts, or where it is that the graph crosses the y-axis, set x equal to 0, and we have to solve for y. So let's go ahead and put everything all together. Let's solve for these asymptotes, and let's also solve for these intercepts. Okay, so as mentioned before, we're going to find the asymptotes. The horizontal asymptote was solved previously as y equals 5. And so we can go ahead and plot that right here. Just like that. I represent this with a red line, but when you graph, you can do so with a dotted line if you don't have different colored pens. Now, for the vertical asymptote, we'll take the denominator and we'll set it equal to 0. So we end up with x squared plus 1 equals 0, and then we can do algebra to solve. So let's subtract 1 on both sides, and then we'll end up with x squared equals negative 1. We want to get x by itself. The opposite of the squared that's there is a square root, so we'll square root both sides. When we do so, we end up with this line here. However, before we even continue, there's a big problem. You cannot find the square root of a negative number. It doesn't exist. It's impossible. Therefore, we can stop here and conclude that there are no vertical asymptotes in this case. Okay, let's move forward to the intercepts. For the x-intercept, we'll set the numerator equal to 0. And so we'll have 5x squared equals 0. Solve for x, we get x equals 0. We can plot that point. But not yet. I've already jumped the gun. We have to check if this makes the denominator equal to 0. So let's plug in 0 into the denominator. 0 squared plus 1 equals 1. No, it doesn't make the denominator 0. Therefore, this is valid and we can plot it right there. Now, let's move on to the y-intercept. The y-intercept, what we have to do is set x equal to 0, and then we can solve for y. And so let's do so here. We'll plug in 0 for x, and so we'll get 5 times 0 squared. That equals 0 in the numerator. And then in the denominator, we'll have 0 squared plus 1. That'll equal 1 in the denominator. And 0 divided by 1 is equal to 0. So what we'll end up with is that right there. We have our y-intercept and our x-intercept both at the origin. Same point. Okay. Can we graph? No, not really. We're missing quite a bit of information. And so what it is that we can do is we can plug in values that'll help us to fill in the gaps to actually draw a curve. In this case, it'll vary depending on what your graph looks like, depending on what asymptotes that you have, depending on where your x and y intercepts are. but the general rule of thumb is to just fill in the gaps, find values in between your asymptotes, find values where there's anything missing. So the x values that I choose to use here are going to be to the left and to the right of the origin. So let's say I choose -5, -3, 1, 3, and 5. And so I'll go ahead and plug each of those into the original equation, my 5x squared divided by x squared plus 1. And from my first coordinate, it'll be -5, and my y value will be 4.8. And so I can plot that right there. And I'll do the same thing for the other x values it is that I came up with. I'll take each of those, plug them into the equation. I can use my calculator and I can find the y and plot points. Just like this. Now, this looks more like the pattern it is that we're used to seeing when it comes to graphing. So let's go ahead and connect everything all together. This will end up being a curve, and this fits. Everything hits the x and y intercept at the origin. There's a connector right there, and nothing touches the horizontal asymptote that we solved. There's only one, and so this would be our graph. To recap, today we learned just how complex it is to actually graph these rational expressions, but we figured it out. We were able to determine how to get our vertical and horizontal asymptotes from our functions based on different rules. We were able to solve for the x and y intercepts. Some functions will have them, others won't, depending on what the asymptotes are. And we also learned that sometimes you have to fill in the gaps in the graph because the previously mentioned key elements may not always give you the pattern is that you need to draw a curve. Thank you for watching Effortless Math Channel.